In September 2027, Voyager 1 will mark exactly 202,750 years since the day it left Earth. On that date, at the speed it maintains today, about 61,000 kilometers per hour, it will be at around 176 astronomical units from the Sun. Translating this distance into something you can feel, the light that leaves the Sun, which crosses the entire solar system in a blink, takes about 22 hours to reach Voyager. It's so far away that an order sent from Earth now would only get there almost a day later. And even so, that's still not much. At that same speed, it would take 300 years just to reach the inner edge of the Oort cloud, the icy shell of debris that surrounds the Sun. And it would need 40,000 years to get close to another star. 40,000 years. That's more time than the entire history of human civilization, back and forth several times. Over the next billions of years, where will it go? And what will it see? Before answering that, it's worth taking a step back.
The original mission of Voyager 1,
Together with its twin sister,
Voyager 2,
its mission was to explore the outer planets of the solar system.
Voyager 1
Had a specific task: to closely study Jupiter and Saturn, their moons, and the magnetic fields around them. The route was designed to take it to Jupiter in March 1979 and to Saturn in November 1980. When it arrived at Jupiter, the cameras captured complex cloud patterns, giant storms, and the planet's faint ring system. One of the most striking images was the detailed view of the Great Red Spot, a storm larger than the entire Earth, spinning for centuries. Voyager also looked at Jupiter's moons. It was there that it was discovered that Io is the most volcanically active body in the entire solar system, with erupting volcanoes and rivers of lava flowing across its surface. And the images of Europa revealed a smooth, icy shell, suggesting a liquid ocean hidden just beneath the ice. A year later, Voyager reached Saturn. The images showed the fine structure of the rings, with countless tiny rings and gaps within them, including the previously invisible F ring. Just as it had done with Jupiter's moons, the probe delivered detailed views of Saturn's moons. But perhaps the most important discovery was the thick, orange atmosphere of Titan, Saturn's largest moon. A dense atmosphere rich in nitrogen and hydrocarbons, suggesting the presence of complex organic molecules. A chemistry similar, in some ways, to what existed on Earth before life began. Almost a decade later, in 1990, Voyager 1 entered the extended phase of its journey, known as the Interstellar mission. The goal now was to explore the outermost edge of the Sun's domain, the heliosphere, and then cross over into interstellar space. It was during this phase that it took the famous photo of the pale blue dot, the entire Earth reduced to a pixel lost in a ray of light. 8 years after that, it surpassed the Pioneer 10 probe and officially became the most distant object ever built by human hands. This happened on February 17, 1998, when Voyager was about 69 astronomical units from the Sun, which is around 10 billion kilometers. And on August 25, 2012, almost 15 years later, it crossed the heliopause and entered interstellar space. It was, officially, the first time that a human-made object directly measured cosmic rays, magnetic fields, and the density of matter at such a distance. Among the stars, the first numerical reports of what exists in the gap between one sun and the next. Voyager maintains contact with Earth using a high-gain antenna that's almost 4 meters in diameter. This antenna focuses the radio waves into a narrow beam, which allows it to send and receive signals over absurd distances. It communicates with a network of giant antennas spread across California, Spain, and Australia, positioned about 120 degrees apart from each other around the globe. That way, as the Earth rotates, there's always at least one antenna facing the probe. The signal travels at the speed of light, and today it takes about 20 hours to reach us. The probe's energy comes from generators that turn into electricity, the heat released by the decay of radioactive plutonium. These generators have a half-life of almost 88 years and lose about 4 watts of power each year. It's a candle that burns out slowly. The scientific instruments are being turned off to save what's left. And in the next few years, the last one will go silent. After that, Voyager will continue its journey in silence, but no new signal will arrive. It becomes what it was always destined to be, a silent object crossing the darkness. Still, it isn't traveling empty. Voyager carries a gold-plated copper disc with sounds and images chosen to portray the diversity of life and culture on Earth. A time capsule made for any form of life or any human in the future who may one day find it. It has greetings in 55 languages, music from various cultures and eras, natural sounds from the planet, and images of life and the human condition. A note written by an entire species, addressed to no one in particular. So, how far can Voyager go? In practice, given its trajectory and the vastness of space, it's much more likely that it will experience slow wear over time from impacts by micrometeoroids, cosmic radiation, and temperature cycles, than for it to be captured by the gravity of some star or planet. Its structure could remain recognizable for hundreds of millions, maybe even a few billion years, as long as it doesn't hit anything big. In all that time, it will have traveled about a quintillion kilometers. And even so, that's less than 2% of the diameter of the Milky Way. It will pass far from thousands, maybe tens of thousands of stars, heading toward the constellation Ophiuchus, crossing the regions of Hercules, Lyra, Cygnus, and Draco. Never close enough to land, always just passing by. But over billions of years, the route itself will change. The gravity of gas clouds, passing stars, and the tidal forces of the entire galactic disk will slowly twist its trajectory. The stars you see today will have moved to other places. The constellations we know will have broken apart. New stars will have been born. Old ones will have died. The galaxy of the distant future will look almost nothing like the one we have now. Predicting Voyager's exact path stops being a matter of physics and becomes a matter of probability. It will be carried by the ocean current that changes shape. And this is where this story stops being about a machine and starts being about us. Because Voyager is the farthest thing humanity has ever sent anywhere, it's our record, the longest arm our species has ever stretched out into the cosmos. It took 35 years of engineering just for it to cross the boundary of the solar wind. And despite all that, it still hasn't truly left the solar system. That's the part almost nobody gets right. And that's the part that took me the longest to accept. When the newspapers said in 2012 that Voyager had left the solar system, that's not exactly true. It left the heliosphere, the bubble blown by the sun. But the real solar system goes way beyond that, all the way to the outer edge of the Oort cloud. And at that speed, Voyager will only leave the Oort cloud in about 30,000 years. 30,000 years just to finish crossing the sun's own backyard. Our fastest probe, dead, with no weight to carry back, will still take all that time just to leave home. Which brings me to the question that gives this whole thing its title. If our best machine, which doesn't need to breathe, eat, or come back, barely drags itself out of our own system, what can we say about the human body, made of flesh, bone, water, and memory? The honest answer, when you follow physics all the way to the end, is uncomfortable. That's how the video got its name. Why will humanity never leave the solar system? It's not pessimism. It's not a lack of will. It's not because we're missing some technology that might be invented someday. It's the structure of reality saying no. And it's possible to show this step by step. No drama, just with the numbers. Start with the distance. The closest star to the sun is called Proxima Centauri. It's about 4.25 light years away from here. In kilometers, that's about 40 trillion kilometers. 4 followed by 13 zeros. There's a way to feel that number, which is kind of brutal. If the sun shrank to the size of an orange on a table, the Earth would be a grain of sand about 10 meters away. Jupiter, a little ball, 50 meters away. And Proxima Centauri, the nearest orange, would be more than 2,000 kilometers away. 2 oranges separated by the distance between 2 cities, and nothing, absolutely nothing, in between. The space between the stars isn't just far, it's a whole different category of far. At Voyager speed, that same 61,000 kilometers per hour, which is already the fastest thing humanity has ever launched. To leave the system and reach Proxima Centauri, it would take more than 70,000 years. 70,000 years. Writing, the wheel, the pyramids, the internet, everything humanity has done has happened in just the last few thousand years. 70,000 years is a chasm of time that our entire species can barely imagine. And that's just to reach the neighboring star, the closest one of all. And we can't fool ourselves into thinking that humanity has already gone far. The truth is almost embarrassing. In all of history, only 24 people have traveled beyond low Earth orbit, and all of them went toward the moon. The farthest point a human being has ever reached is about 400,000 kilometers from here. That's the record held by the crew of an Apollo mission that had to go around the moon. 400,000 kilometers. Voyager has already traveled billions of times that distance. The greatest distance a human body has ever been from Earth would fit entirely in the gap between the Earth and the moon. That's the real reach of the human arm in the cosmos, without the help of machines. It barely leaves home. And the worst part isn't even the distance itself. It's what exists in between. Nothing. Between the sun and Proxima Centauri, there are no gas stations, no islands to rest, no ports to repair the hull. It's pure vacuum for 40 trillion kilometers. If something went wrong along the way, there would be no help. A call for help sent from the middle of the journey would take years just to reach Earth. And the answer? More years to get back to a ship that, by then, would have already moved on. In the real ocean, a castaway can still dream of a ship on the horizon. In this ocean, the horizon is thousands of years away in every direction. Then comes the natural reaction. So just build something faster. And this is exactly where physics closes the first door. In 1903, a Russian school teacher named Konstantin Tsiolkovsky wrote the equation that governs any rocket that has ever been or ever will be built. The idea behind it is simple to grasp, even without the math. A rocket moves by throwing mass backward. To go faster, it needs to throw more mass. But that mass is fuel, and fuel has weight. So to carry more fuel, you need even more fuel just to push the fuel you just added. That snowballs mercilessly. It's not that it gets difficult, it gets exponential. Every little bit of extra speed requires far more fuel than the previous increment. With the chemical rockets we have today, the same ones that take people to orbit, to accelerate a spacecraft to just a tenth of the speed of light, you would need more fuel than there is matter in the observable universe. Not in a country, not on a planet, in the entire universe. I confess that it took me years to really accept that. For a long time, I thought it was an engineering problem, one of those things we solve with time and money, like what happened with airplanes and computers. But it's not. The rocket equation isn't a limitation of our spacecraft. It's a consequence of how thrust works. You could be the most advanced civilization in the galaxy, and the same snowball effect still applies. The barrier is in the laws of physics, not in the engineer's skill. And here's where a common confusion usually comes up. Someone might point out that humanity has already built things much faster than Voyager, and it's true. The fastest probe ever made reaches almost 700,000 kilometers per hour. But it gains all that speed by falling toward the sun, pulled by its gravity, skimming close to the surface. It's borrowed speed which is used to dive inward, not to go outward. To leave the system toward the stars, climbing against the sun's gravity well, the calculation goes back to exactly what the rocket equation says. Being fast near the sun is not the same as being fast toward the stars. They are two different problems. And the second one is the one that doesn't have a cheap solution. And even if, by some miracle, we invented a way to ignore this barrier and got close to the speed of light, there's still a second door. And this one is the most definitive of all. In 1905, Einstein showed that the speed of light isn't just fast, it's the limit. 300,000 kilometers per second, period. Nothing with mass can reach that speed, not even in theory. The closer you get to it, the more energy you need to accelerate just a little bit more, until, to actually reach the speed of light, you would need infinite energy. And infinite energy doesn't exist. That was also something that took a while to make sense to me. For a while, I thought of the speed of light like a speed limit on a highway, a sign that, with the right car, someone could one day exceed. That's not it. The speed of light isn't a limit imposed on movement. It's part of the very shape of space and time themselves. It's how the geometry of reality is stitched together. You can't go faster than light for the same reason you can't walk farther north than the North Pole. Once you get there, that's it. There's no direction to keep going. And this is where the scale that seals the argument comes in. Even if a spaceship traveled at the speed of light itself, the absolute maximum allowed by the universe, it would take more than 4 years just to reach Proxima Centauri. The entire galaxy is about 100,000 light years from end to end. 100,000 years traveling at the maximum speed of reality just to cross our own galaxy, one among trillions. The universe isn't too big for us by accident. It's too big by exactly the measure that light is too slow. And our galaxy is just one. Beside it, at a distance, float others, billions of them, each with its own billions of suns, separated by gaps that are even emptier and wider. The light that leaves the nearest large galaxy to ours travels for 2.5 million years before it touches a human eye. When that light left there was still no one on Earth we would call human. The universe was not built on the scale of a lifetime, nor of a civilization, nor of an entire species. It was built on a scale where humanity, from the first fire until now, is a blink that hasn't even finished yet. Feynman had a way of saying that nature's imagination is much greater than ours, that it always comes up with things stranger than anyone could come up with on their own. And maybe the strangest thing it could come up with is just this: a universe overflowing with places to go, and no road that any living body can travel to reach them. So the obvious solution would be to accept the slow pace. If you can't go fast, go slow, with a huge ship, a ship that's a city, where entire generations are born, live, and die along the way. That's the idea behind generation ships. It's beautiful on paper. But this is where the problem stops being about physics and becomes something stranger, almost existential. And this journey, when you look closely, is more burdensome than it looks on paper. The first people board knowing they will never arrive. They will grow old and die inside a metal cylinder in the void. Their children are born already in motion and will never set foot on Earth. The grandchildren, the great-grandchildren, a chain of generations who only know the world through stories and images on a screen. People who are born in a can, live in a can, and are buried in the space between two stars, without ever having seen a real sky, without rain, without a horizon, without an ocean. And then there's a question that hangs in the air and nobody really answers. If, after thousands of years, some descendants finally land on a planet around another star, was it humanity that left the solar system? Or was it just a handful of exiled people, so distant from Earth in time and blood that they're almost something else? Those who arrive never knew the place they left from. They don't go back home. They don't have a home. Home has become a legend. And even if, instead of a slow ship, there was a truly fast ship, close to the speed of light, the problem doesn't go away. It just takes a different form. Because near that speed, time passes differently for those who travel. Einstein showed this too. For the crew members, the journey could last only a few years, but on Earth, decades or even centuries would pass. They would arrive on the other side almost without aging, yes, but the Earth they left behind would no longer exist. Their parents, friends, country, language, everything buried by time. There would be no one to send news to, no home to call back to. Relativity turns interstellar travel into a one-way exile, not just in space, but in time. You wouldn't just be traveling far away, you would be traveling to the future. And keeping people alive for centuries in a can is an engineering problem with no margin for error. On a ship like that, everything has to work in a perfect cycle. Every drop of water you drink has to become clean water again. Every breath has to be recycled. Every gram of food comes from plants that grow from recycled leftovers, year after year, generation after generation, without ever receiving anything from outside. On Earth, the entire planet does this work for free, with oceans, forests, and a vast atmosphere cushioning any failure. In a can in a vacuum, there is no buffer. A system that breaks and isn't fixed in time doesn't kill a few. It kills everyone and ends the journey in the middle of nowhere, centuries away from help, which, in any case, would take centuries more to arrive. And then there's the body, that detail we always forget when we dream about spaceships. Because it's not just distance and time that are against us, it's our own flesh. The human body was shaped over hundreds of millions of years of evolution to function in a very specific place, the surface of the Earth, with the right gravity, the right air, the right temperature, and, most importantly, under two invisible shields, the planet's magnetic field and the sun's own heliosphere, that same bubble that Voyager took 35 years to cross. These two shields deflect most of the cosmic radiation that travels through space. And there's a way of looking at the human body that changes everything. We aren't just made on Earth. We are made from the Earth and for the Earth, adjusted to it in every detail. The amount of force our bones can withstand, the rhythm of the heart, the way blood is distributed, the thickness of the skin against the sun. We are creatures of a single star, shaped by its heat, protected by its field, bound to the ground of a single planet by the same gravity that gave us form. Taking this body into deep space isn't just taking a traveler on a journey. It's like pulling a fish out of water and asking it to learn to fly along the way. On the outside, without this protection, the body is exposed to a constant drizzle of extremely high-energy particles. The galactic cosmic rays which pass through the skin, the metal of the spacecraft, and tear through genetic material cell by cell. On a journey lasting decades or centuries, this isn't a risk, it's a certainty. Add to that the loss of bone and muscle that we already see after just a few months in weightlessness, and the picture is of an organism that simply wasn't made to exist out there. And it's not just the human body that suffers. The ship itself suffers too. The space between the stars seems empty, but it isn't. It's full of loose hydrogen atoms and tiny grains of dust. When they're still, they're harmless. But when a ship travels through this medium at a fraction of the speed of light, each of those atoms becomes a projectile. A single grain of dust, the size of a smoke particle, hitting the ship at that speed carries the energy of a small explosion. On a journey lasting years, the front of the ship would be sanded down, punctured, and corroded by a never-ending bombardment. Going slow takes too much time. Going fast means being destroyed by your own body. The universe charges a toll at both ends. And here I'm going to openly disagree with an idea that has become almost a religion in recent years. The idea that humanity's becoming an interstellar species is just a matter of time, willpower, and ambition. That all it takes is to dream big enough. I think this story is beautiful, and I understand why it brings comfort. But it deliberately ignores the rocket equation, the speed of light limit, and the fragility of the body. It's not defeatism to acknowledge a barrier, it's honesty. And deep down, there's something almost more beautiful about facing the limit head-on than pretending it doesn't exist. Of course, when someone gets to this point, the final card gets played. What about the impossible ships? Antimatter, warp drive, wormholes? It's worth taking a closer look at each of them because they're real as physics concepts. But each one runs into the same difficulty. Antimatter is the most powerful fuel known to physics. When it comes into contact with ordinary matter, both annihilate each other and turn into pure energy with almost no waste. A spacecraft powered by antimatter would, in theory, be the perfect engine. The problem is producing the fuel. In decades of work in the world's largest laboratories, all of humanity has produced, in total, an amount of antimatter smaller than a few billionths of a gram. To power a real spacecraft, you would need kilograms. At the current rate, producing a single gram would take longer than the age of the universe and would cost more than the entire economy of the planet. Then there's the warp drive, the famous idea of bending space instead of traveling through it. In 1994, the physicist Miguel Alcubierre showed that within Einstein's equations, there is a mathematical solution for this. A bubble that compresses space in front of the ship and stretches it behind so that the ship, stationary inside the bubble, would be carried faster than light without breaking any rules. On paper, it works, but the price is out of this world. Literally, to bend space like that, you would need a form of matter with negative energy, something that might not even exist in nature. And the amount of it, according to the initial calculations, was comparable to the mass of the entire observable universe. Later calculations reduced that number, but it's still enormous, and it still depends on a type of matter that no one has ever seen, touched, or proven to exist. The warp drive is not a ship that just needs to be built. It's a beautiful equation, waiting for ingredients that maybe the universe simply doesn't have. And what about wormholes? Here, I need to be honest about what science still doesn't know. The equations allow them to exist. Tunnels that would link two distant points in space through a shortcut. But no one has ever observed them. And even if they did exist, everything indicates that they would be unstable, closing in an instant, or that they would need, again, that same negative energy matter to stay open. I'm not going to pretend that I'm sure it's impossible forever. No one is. But turning a fragile, theoretical possibility into an escape plan is confusing what physics allows on paper with what nature delivers in practice. And those are very different things. There is, to be fair, a single interstellar plan that real physics actually allows. The idea is to abandon the rocket altogether. Instead of carrying fuel, you build an ultra-thin sail, lighter than a sheet of paper, and push it from afar with a powerful laser beam fired from Earth. With no fuel on board, the rocket equation loses its power. And this sail could, in theory, reach a fifth of the speed of light and get to Proxima Centauri in about 20 years. For a second, it seems like the way out of everything that's been said so far. Until you look at the size of the thing. Because what this sail can carry is not a person. It's not even a chair. It's a chip, smaller than a stamp, with a tiny camera and radio. No crew, no supplies, no return. And going at a fifth the speed of light, it wouldn't be able to slow down. It would fly past the other star in a matter of hours, taking a few pictures before disappearing into the darkness on the other side, forever. So the most realistic interstellar plan humanity has today is to launch something smaller than a fingernail that doesn't stop, doesn't come back, and none of us could ever see with our own eyes. It's a perfect picture of the limits of our reach. We might be able to catch a glimpse of the opposite shore.
Crossing over to it our bodies, with people, with a place to call home on the other side.
That's what the
Laws don't allow.
And even that opposite shore might not want us either. In 2016, astronomers discovered that there is a planet about the size of Earth orbiting Proxima Centauri at just the right distance to have liquid water. For a moment, it seemed like a second home waiting for us. But its star is not a calm sun like ours. It's an unstable red dwarf that frequently releases violent bursts of radiation, bathing this planet in doses that would likely sterilize any exposed surface. The closest neighbor that exists, the easiest of all, already comes with a no entry sign on the door. And that's the best case scenario, the most inviting one. After that, it's only darker and farther away. And it's worth thinking about what would happen even to a simple probe we managed to send there. It would be alone in a way that none of our machines have ever been. A command sent from Earth would take more than 4 years to arrive. And the response, more than 4 years to come back. More than 8 years between a question and its echo. There's no way to pilot something like this. There's no way to fix a malfunction in time. The probe would have to decide everything on its own, in the dark, too far away for any help to make sense. And that's still the easy version of the problem, because it's just a machine. When you replace the machine with people, the last safety net that distance still allowed disappears. The company of those who stayed behind. When you put all this together, the distance, the rocket equation, the speed of light limit, the time of generations, the fragility of the body, and the exotic dreams that always run into the same wall, what remains is an image that's hard to accept. That maybe the solar system is not the cradle of humanity. Maybe it's her entire world, from beginning to end. And the hardest part is that there's a clock ticking. The sun won't shine like this forever. About 1 billion years from now, it will be hot enough to boil Earth's oceans. In about 5 billion years, it will swell into a red giant and swallow the closest planets, maybe ours too. Life on Earth has an expiration date, and that date is written in the physics of a star. The natural solution for any species that wanted to last would be to move to another system before the sun itself wiped it out. And that solution is precisely the one that distance, light, and the body have made almost impossible. An eviction notice with a set date and the only door locked from the outside by the laws of the universe. An ancient and silent library. Carl Sagan had a beautiful way of saying this. He called space the cosmic ocean and our neighborhood of stars a beach at the edge of that ocean. We were born on that beach. We learned to make little boats that reach the surf, probes Voyager that venture a few meters out to sea. But the real ocean, the crossing to the other shore, is so vast that our lives, our bodies, and our physical laws were not made to overcome it. There's something that Feynman liked to point out, in his own way, a bit impatient with those who fool themselves, that nature has no obligation whatsoever to be the way humanity wishes it were. The universe doesn't owe anyone the stars. We can wish, dream, calculate, but if physics says that the gap between the suns is too big for a body of flesh to cross, then it's just too big. Accepting that isn't giving up, it's maturing. And this is where the story takes a turn and stops being sad. Because there's something strangely comforting about truly understanding that. If humanity, in the flesh, may never leave the solar system, a part of us already has. It's out there right now, traveling through the darkness at 61,000 kilometers per hour.
Voyager. A dead, silent machine. Blind. Crossing a void that none of us will ever see. Carrying a golden record with children's laughter. With music. With greetings in 55 languages. With the sound of a storm. And with a beating heart. She will continue when the antennas go silent. It will continue when the last person who worked on it no longer exists. It will probably continue even when the sun itself is gone. When the constellations in the sky have dissolved into other forms.
Maybe that's the only way for humanity to really leave this place. Not in ships with people inside, arriving triumphantly on another world. But like this, silent. A golden metal note more enduring than the species that wrote it. Traveling for billions of years with a single message engraved. Spoken by an entire planet to a universe that may never listen. We were here. We looked up. And for a very brief moment, on this shore at the edge of the cosmic ocean, we wondered what was on the other side.